start formation which does not go through a hierarchy phase, as the textbooks tell you. So I think that will be interesting. And that means, so next week I'm away, and maybe that is a good idea if Leonid can talk about our joint work on the causalicity. Mm-hmm. That would be interesting because it has some connection with solar observations, and we can even get some solar people there. And I think it's good if you have a lot of activity even when I'm not there. Okay. So the background for working on the Fisher equation, it has to do with the fact that it actually processes propagating front solutions, and it's in that sense a simple model of understanding some aspects of turbulent combustion. Turbulent combustion, and there's different ways of turbulent combustion. In particular, the thing called pre-mixed turbulent combustion. So that means fuel and the oxidant are being locally already mixed. And you just put a match on one side, and when you put a match on one side, everything is in principle can burn. And really doesn't have to wait for the turbulence to bring in the fuel. And so then you have a turbulent front which just goes across the domain. This is here actually a solution of this Fisher equation in 3 dimensions already in the background. So this Fisher equation, which I didn't write down now, come. That was because probably people assumed that they know that. Let me just take a look here. Yeah, maybe that's good enough here. I should maybe start this with this one here. So the Fisher equation is an equation for one scalar quantity in C by dt. It has a dissipation term. It's in this case one-dimensional, and it has a non-linear term. So just, first of all, it has a linear part of it. It corresponds to an exponential growth. This is a time scale, this is a growth rate of 1 over tau c. It's called the chemical time. But then once c reaches, it goes from 0 to some value that goes to c0, this quenching time will kick in and the growth will become quenched. And so this is an equation which possesses front solutions of the type x minus ct, and the front speed is given by twice the square root of the dissipation or the diffusion coefficient divided by this tau c. And that's quite remarkable that you have a constant propagation speed from the diffusion equation. Now, with the diffusion, you are thinking it needs to 1 over square root of t time behavior, but in this case, it needs to propagating fronts. And it's well known, in particular in the biophysics and bio community, and it has been modeled, used to model, for example, the spread of the Black Death through medieval times across Europe. 1348, 39, and 50. It's quite interesting to read about the Black Death on Wikipedia, by the way. Anyway, so it has these nice fronts, and then when we go to these 3-dimensional simulations here, it shows you that it ignites this on the one end, and you have periodic, it's a driven turbulence in the background, and on top of that, we run this dc by dt equation, which is basically like a partial scalar equation, but with this reaction term. You have this propagating front thing at a certain speed. Now the question, and we have here the same thing for a different 1 over tau. Lambda is the same as 1 over tau. So in the other plot, it's just slightly faster reaction speed. So the turbulent front will propagate quickly across the domain. So the question now is, how is the speed in a turbulent system? So if you know, of course, if I talk when I talk about this equation, here there's no turbulence at all. So what happens when we turbulence? And of course, we would all think that the diffusion becomes renormalized by turbulent diffusion. And so that's basically the question then. So let me then jump to the early page here, number 2, where the front speed, so the combustion people always call speed not v, as we all used to, but they call speed s for speed. That's why they have this s all the time. And L means dominant, because the turbulence. And so this is the equation I had before, there's a factor 2, simply omitted. And And so the idea is then that if you go from laminar to turbulent state, you just replace d by dt. And of course, some of us who are familiar with this kind of business may already recognize that this can be proposed, which are familiar to us, but they were not familiar to the combustion people. Except they actually knew about it. They didn't know why. So, okay, so this is what, it's not that. You see, I think I have this right plot here, this one. So in fact, they knew that yes. I mean, actually, I think they still didn't really know it because that's what they plot. So what they normally plot is the sphere of the turbulent flame speed relative to the laminar flame speed. And they plot it as a function of the turbulent RMS velocity v prime divided by the laminar front speed. That's to do with the difference. And as you increase the amount of turbulence, you increase the speed of the front. And there was a number of different models, and none of them really agree with each other. This W85 is Williamson, is the famous Williamson, who was also at our program here, and that's from his textbook, and it's one of these from it's, I think, this from there. And then Jacob, 88, had this equation, based on renormalization group approach. And then there is another idea that it could be this equation, where n is a free parameter. If it's 1, then the curve looks like this, and if n is equal like this. And so the measurements cannot really tell which one is right. And I think the reason for this big confusion is because we are all the time talking about different systems, and the real physics can be quite complicated. If you have a front and you have ignition, it leads, of course, to heating. And then once you start heating and you do everything realistically, everything changes in the system. And by the way, Natalia Bhattacharya, who is, of course, on this work, she submitted another paper in the meantime, or prior to this, and that paper now got accepted by the Journal of Computational Fluids. So therefore you have realistic hydrogen combustion with oxygen involving some 20 reactions. But it's not astrophysics, it's real burning of hydrogen and a hydrogen burning bus for a car or something like this. So, so let me then come to this equation. So this brings some of us at least back on track again. Maybe, right, you see that go through this page here. So this is what some of us may know and remember. This is the standard diffusion equation with some kind of a flux. It's a turbulent flux. And the turbulent flux normally is given by the negative Bragg-Hickian diffusion law. So the flux is given by tau times v squared, which is the turbulent diffusivity, times the gradient of the concentration. However, if you, depending on how you calculate these turbulent transport coefficients, if you do it using the power approximation, you begin by writing down the time derivative of the flux, d by dt of u times c, and in that case, you have the time derivative, and you pick up this as the from the linear theory already, and then you have higher order terms. For the higher order terms, you make an approximation. The approximation is exactly what is behind the power approximation, namely that we say triple correlations, which is what this comes from. Triple correlations are being replaced by quadratic correlations, and this one is the simplest quadratic correlation. This has so far no basis, no real basis, but it is consistent with numerical simulations, as we have already shown in 2004. So it's, even though it's not exactly clear that it should be right, it's at least remarkably confirmable with simulations. And so, of course, if you retain this time derivative now, that's actually not really part of the standard power approximation. And I think it was really Eric Blackman in also 2003 who proposed that one should actually retain this time derivative, which people thought is rather crazy, because now you want to calculate these transport coefficients in the steady state. And if you have a steady state, then of course there's no time derivative. We had this discussion earlier this morning with Leonid, where we were talking about a dynamo, and the dynamo leads to growth. Once you have a growth, of course, you have no longer a stationary situation, and so you should be careful about whether you do neglect this thing or not. And so here in turbulent combustion, we have the same thing. We have a front which is propagating through the domain. So is that a steady thing? Of course not. And therefore, you have to retain this time derivative. Once you retain this time derivative, the diffusion equation is actually not of this ordinary equation. It's not a time derivative is equal to the second derivative in space, but it becomes a dense wave equation. So, and of course, so that means, for example, that instead of having a Gaussian propagating it, I don't think I have this included here. Instead of having a Gaussian, in the extreme case where this term becomes dominant, you actually have fronts propagating outwards. And that means, unlike a solution of this equation, which has infinite support, you have a small perturbation, of course, a solution to such a parabolic equation is having infinite support. So you have immediately perturbation at infinity. Unlike that situation, this equation has, of course, only finite propagation speed, namely the speed of the turbulence, which is a third times u squared. So that's so the turbulent diffusion should never propagate faster than the RMS velocity divided by the square of speed. So when you do this kind of thing in a black hole, for example, people don't normally do this. In fact, they have non-causality near a black hole because of the turbulent diffusion, or even just macroscopic diffusion. That's just because they didn't know about this second order condition. So now we know about this, and we checked this, of course, in this earlier 2004 paper, that it makes sense. So there is indeed from direct turbulence simulations, you have direct evidence for this oscillatory behavior, even in turbulence. So then we go to nothing. Here we go. So this is now our equation. So we have the time derivative, now we have the second time derivative here. Here we have the Fisher term, here we have the turbulent diffusion term. It becomes slightly more complicated, and I may or may not be able to say more why. Sorry, this was the turbulent diffusion term. And this one is also a completely new term yet, and we have not fully understood this yet. So there's indeed another effect from the non-linearity of this reaction term. That leads to the appearance of a new heating term, and I don't have the blue graphs ready for that, for which you can do mean field theory. But once, depending on how short this time scale is, depending on how short this time scale is, how efficient this can actually change sign, and it would actually also mean that this potentially can change sign. So that is probably not indicating that something would not be right in such a case in the series. So we have really, for most of it, ignored it. We have studied this kind of how it would affect this. But let me stick first of all to the effect of this term here. And here you see the effect in a way that becomes now most obvious. If you have turbulent diffusion, and there's this parameter called the W-Taylor number, which is, where is it now defined? It's of course just a measure of tau c. Let's write it down. The W-Taylor number is measuring, it's a non-dimensional measure of our quantity tau c. So tau c times u RMS, the turbulence, times the force inversion of the turbulence. So this is in some sense the turnover time of the turbulence, tau turnover, divided by tau chemical. So the chemical time is short. The chemical reactions happen quickly compared to the turbulence, and the Dunkelman number becomes large. So for small Dunkelman numbers, what we find is that the turbulent front speed increases with the square root of the turbulent velocity. No, it's proportional to so in this earlier regime at least, the standard equation still holds. So in other words, the turbulent front speed as turbulent is equal to the square root of U R S squared times tau, of course. So it is proportional to URMS. And then, of course, if you normalize for another. I don't know, it's very nice. But once one gets so deeply involved, one understands everything at the moment, of course. Once the whole thing was 2 months ago, this was in May. It's no longer completely clear in my head. This is, of course, the equation for how speed, and we normalize by UMS, and then you would think it's sorry, yeah. Okay, we have. I don't think I have that here. So then I would need to, these are of course the equations that I have. After that. No. Then I don't think they eliminate it, just because it's pretty, of course. And the effect of large Dunkeln numbers, of course, is that the Dunn speed propagates, and it doesn't become, it doesn't go faster than the turbulence goes. Still, you'd be surprised.
What is the problem?
Yeah. So my problem now is that according to this, I'm thinking that the turbulent Dunn speed is probably the RMS velocity. But of course, if I normalize by the RMS velocity, that should be a unity values independent of anything. But I think I'm missing the problem here. So I shouldn't do this, but I should replace this by URMS divided by this one instead. And if I then normalize this, then now divided by URMS, the difference between the prime and URMS is just square root of 2. Then of course I have something which is that would be decreasing.
But what's the problems with that plot?
There's hopefully no problem with the plot. It's just hopefully the problem in my head. In the sense that I'm able to explain you why the ratio of the turbulence velocity divided by the RMS velocity is increasing
With the
system to the slope was a half, right?
Yes, the slope is a half.
Yes. Okay. But a half for the first, but it's this is should actually decrease from
What's the down point number again?
Yes. Right. Okay. Exactly. So therefore you find yes, exactly. So therefore you find that square by the number of square of UMS. And that is 1 over the square of Dunkeln number. No, sorry, it's the square of Dunkeln number. Okay, that's what we found. Okay, so this is what you would expect. So you would expect this curve to go, but then it doesn't. And the reason why it doesn't at large Dunkeln numbers anymore is because when the Dunkeln number becomes large, this the tunnel time becomes very, very long compared to the reaction time. So in other words, during the time that the turbulence does something, in the chemistry, it's reacting much, much faster. And that, because of that, turbulent transport becomes essentially quenched. So this turbulent transport coefficient does effectively more than that work. And therefore, this saturation. And I think this plot is much clearer plot than the plot that we have seen previously by the combustion people.
Does it saturate the laminar speed?
No, it's fast. It's still faster than the laminar speed.
It's still faster.
Yeah. By a certain value, which has to do with how fast the laminar speed was. Yeah. Okay. Sorry, and then we compare, of course, against the previous formulae. This was maybe the best case scenario, remember that we had these 4 different formulas in the beginning, but this is then our new formula. This is based on analyzing, first of all, this model equation, which we can run quite easily, and we can find fits to the solutions. So this is not an analytic solution, but it's actually an extremely accurate fit to the equation. Actually, if you look here what you see points from the numerical calculation, this is one-dimensional PDE. And then we simply guess a fit, an analytic formula which describes this. In the studying such a fit, of course, everything can be described in terms of analytic fit formulae. If you do this, you find this expression. So you find a p-factor which depends on a quantity called the Storen number. It also depends, epsilon again. This is a U, of course. This is equivalent Chomsky divided by lambda Chomsky, and epsilon is a factor which has to do with the square. I think it's a ratio of, it's another quantity again.
It's your third line.
It says that, yes. Good. It's a ratio of the dissipation length divided by the flame width. The flame width has to do with the square of the dissipation multiplied by pi. That is the length square of course. It's the thickness of the flame. It's the thickness of the flame, yes. And that is what people in the combustion community call it. Okay, so we are pretty close to the first formula, but this is not quite even accurate. The more disappointing situation comes, of course, when we actually compare now against our three-dimensional simulations. Because when we do that, we find that the data points that we get from the simulations describe, they lie roughly in such plots. This was the second plot for finite packing number. It shows the saturation case in the previous plot for infinite packing number first, and then the right-hand side shows for finite packing numbers. If we have finite packing numbers, this saturation becomes linear again at higher Planck numbers, depending on how small or big the packing number is. Packing at large packing numbers, of course, we have in realistic situations. Now, in our simulations, we believe actually that the packing numbers were, in some cases, on the order of 100. So they were not as small as below 10, but they were certainly above 10. So there seems to be some quantitative mismatch, but not exactly qualitative mismatch between simulation and model. And here we see the plot of the equivalent points to relate. So this is actually the standard plot which people in the community always plot. Prevalent over lambda Chomsky versus RMS losses equivalent divided by lambda Chomsky. And again, we see that the data points are roughly around a ratio of the dissipation length to the front thickness, which is around 10. And according to our estimates from the direct simulations, it should be in context of the larger. But there's also a big scatter, which is maybe also somewhat disappointing. But that's the best we can do so far, and of course we thought at some point we better stop here to wait that other people have to come up with. That's basically the situation with that paper, and we have no report on that yet.
So what is the difference in the symbols?
These are actually different packing numbers. And mostly the different packing numbers. They all have good enough resolution up to 256 and the back. 256 in the square direction, in some cases longer along the front direction. Yeah.
Because the packing number expanding the same way as the lines are.
They are occupied somewhat, yes. So the bigger the symbol, the bigger the packing number. And the largest ones should be actually around 100. So that is not degree figure. And so, but on the other hand, one reason maybe why there could be still disagreement is because in all those plots here, we ignored actually this time. So there is a as I said, there's a renormalization happening from this chemistry. So there's this, you write across the C bar plus little c, and you end up with the quantity that we call H, which is little c squared average. So you have to have an infield theory for that, and you write that, and you find that it should be proportional to the flux times the gradient of the concentration. It's a certain sign, with a certain P factor. And then this P factor can change sign. And of course, if you then approximate the flux by the gradient of C, you find that this term should be proportional to the gradient of the concentration squared. And I think that's a qualitatively new thing. By the way, it also means that if you put this back into the equation, so this equation, if you put it back into the original evolution equation, actually you can write it the following form. You can write it as an n dot c. So n is now, let me call it u, v, because u is velocity. So v is something else. V is of course double velocity. And so this v now is equal to the gradient of c. That is somewhat really better for you. No? No. I'm thinking of this actually has to do with the G equation. It's in combustion theory, they have a so-called G equation for the propagation of the front. So they have an advection term in the evolution equation. The advection does not happen with this equivalent vector, with the actual velocity, but it happens with the gradient of the concentration itself. However, in that case, it comes with the upward sign. So they have an upward sign. You come to the plus sign. So and of course, it shouldn't be the same because these are completely different things. Because in one case, here we are talking about the so-called flame brush. Flame brush means this broad. So if you have a flame which is like this, then this is what we call the actual flame front, the corrugated flame front. But this whole broad thing is what we call a flame brush. And we are talking about the propagation of the flame brush, whereas the other guys are talking about the propagation of this set, which goes always in different direction with it. And that is indeed described by such an equation that we cannot calculate time. So yeah, I think there are still some open questions to be addressed, but of course at some point we thought we should stop and come back to dynamic theory, of course. Okay, questions? Now we have this colloquium, and the title of the colloquium, remember, is it's not G modes, but it's gravity waves, gravitational waves. So one is gravity waves, the other one is gravitational waves. And you find it by clicking here and then clicking here. And then clicking here. So that's coming up, and there will be more coffee at the entrance of this time, of course.
No envelope visibility, right?
What?
There could be no envelope visibility, right?